This is section 3.6, number 9. Find the solution of the initial value problem. The second derivative of y minus 4 times the first derivative of y plus 13y equals 0. This wouldn't satisfy, we couldn't call this a damped harmonic oscillator because this coefficient b is negative, and we're not going to have negative damping. Still, it's a valid second order differential equation. The initial condition is its position at time 0 is 1, its velocity at time 0 is negative 4. Characteristic polynomial produces two complex values. We only need one of them. We could choose 2 minus 3i or 2 plus 3i. I tend to always choose 2 plus 3i. So our solution looks like e raised to the 2 plus 3i, which can be written using Euler's formula as e to the 2t cosine 3t plus I sine 3t. Distributing the e to the 2t, we have a real component. This part is the real part. Y of t is a complex valued function. This would be called the real part of y, and this would be called the imaginary part of y. But note that the imaginary part of y has no i's in it. It is a real valued function. Note that y of t is a complex valued function that solves this differential equation star, and that implies that both its real part and its imaginary part also solve y. And you should try that. You should take this function, take its second derivative, subtract 4 times its first derivative, and add 13 times the function, and you'll see that everything cancels and adds up to be 0. So both of these are solutions. So we have two solutions, y sub 1 and y sub 2, made up of the real part and the imaginary part of this expression. So the general solution will just be a linear combination of these two solutions, k1 times y1 plus k2 times y2. On the next, in step 3, we are going to need the velocity. Since we have position, dy dt, the derivative of dy dt is the velocity. So we differentiate the expressions from the previous page. We have a product rule. We have two product rules. You can verify that I believe this is correct. Grouping the e to the 2t cosine terms together and the e to the 2t sine 3t terms together, I get this as a coefficient for v of t, and I get this as a coefficient for, this is a coefficient for this expression, coefficient. Finally, we can now apply the initial conditions from the previous slide. I'm taking, t equal to 0, and the only term that survives is a k1 term. I'll go back to that. Turns out I can't go back to that, so we'll stay right where we are. But you can check for yourself that y at time 0 is k1, and y prime, you can see that here at time 0, the cosine of 3t at time 0 is a 1, e to the 2t is a 1, sine of 3t is a 0, so this entire expression cancels, and we're just left that the velocity at time 0 is just 2k1 plus 3k2, this expression. We're told the velocity is minus 4, position is a 1. Putting our equations together, we see that k1 is a 1, k2 is a minus 2, and then therefore this is our solution of our initial value problem. At time 0, it is a 1, and at time 0, the velocity, if I were to take its derivative, I would see that the velocity is a minus 2. Here's the velocity function. 2 times k1 is a 2, minus 3 times k2. I better check that. Hold on. No, I'm correct. My initial conditions are 1 and minus 4, so at time 0, if k1 is a 1 and k2 is a minus 2, I get a 2 minus 6, which gives me my negative 4. So this is correct, and this is correct, and this is our solution of our initial value problem.